Like any other operating system, Linux provides a multitude of ways of managing users. The most basic way, and the one that's included by default in every distribution, is through file-based user management. There are 4 files included. One is the password file, which we've looked at before. 3 additional ones are one called etc shadow, and that stores primarily password information. There's also an etc group and an etc g shadow, which do the same type of things but for group membership mapping. I'm going to go ahead and go through each of those in turn, and then we'll get a feeling for what the file format looks like. You'll need to know this because if you have to manage users or groups directly, the easiest way is typically by editing the files. Take a look at the now somewhat familiar password file from before. This time I'm going to break down each field. Fields are separated by colons. The first field is the username, and then the second field is traditionally where a password would have been stored. Back in the ancient days, they removed the passwords from this file because even the encrypted version was world-readable and vulnerable to attack. They moved it into a separate file called the shadow file, which we'll explore in a little bit. The third field is the user numeric ID field, and then after that is the group numeric ID field. Next, you'll see is the student, followed by 3 commas. In an enterprise environment, you would see the user's full name, say something like their phone extension, and maybe their office number stored here. The next 2 fields tell the system where to look for the home directory and for the login shell. The shell is the program that's run as the first thing that executes when someone logs in. It's what takes command interpretation and gives input and output to the monitor. Now pay attention to 2 of the numeric ID fields. The first line in the file for root and the last line in the file for student show 2 important differences. In Linux, the name is mostly symbolic, and it's the number, the numeric ID of the account, that actually matters. And in this case, the numeric ID also generates your permissions. The root user is the equivalent of a Windows administrator and has all access to everything. And that's defined by the fact that its user ID is 0. No other user ID has that level of permission, and normally you would never have more than one user ID 0 user on any given system. Compare that to my user, the student user, that has a UID of 1000 instead. Now, with the UID of 1000, it means I don't have any special privileges, but anywhere in the system that student owns a file or directory, it's actually owned by the user ID 1000. This is important because normally system changes can only be done by root, and they won't be able to be done by student. There's a special system in place for that called sudo, which I've shown quickly once. But in general, if you want to do large system modifications, it has to be done by someone with the privileges of UID 0. To show that off, I'm going to once again try to read a file that I'm not supposed to. In this case, it's that shadow password file that I alluded to before that has all of the encrypted versions of the system passwords on it. There, I got a permission denied, which is perfectly understandable and is exactly what we'd expect to happen. Since I can't read the file normally, I'm going to need to find a way to elevate my privilege level in order to read it. In this case, the etc shadow is owned by root, and so I need to have root permissions in order to read it. In comes the command sudo, and sudo will allow me to run a single command as root, just long enough to get the information out of this file that I need. In this case, I'll be running cat as root, and cat with root privileges will be reading the file for me. As it pops up here, you can see in the last line there's a whole bunch of gibberish. What that actually is my encrypted password for the student account. Just to prove it to you and make sure that I'm not making it all up, I'm going to go ahead and change my password using the passwd command. I entered my old password, entered a new one that I thought sounded reasonable, and then I'm going to go ahead and check it again to see that the line has changed. And it has. So that's great, and that's an easy way also to change your password whenever you feel like you need to. In addition to users, we also have groups. Groups give you an extra way to handle user permissions so that you can assign read-write access to a given file or directory to a group, and then any person who is a member of that group has the same access. I can determine what groups I'm a member of by using simply the groups command. As you can see here, it's a short list. It's also the default list that Ubuntu is going to assign to whatever user you create first during the installation. Taking a look at the group file, you can see that it's similar to the password file. It's split into fields. The first field is the group name, then there's an X for where the password might have been, then there's the numeric group ID, and finally any members. So using the student account as an example, we're going to go ahead and check out the group file format. First, let's grep for student inside the group file, and you'll see a listing of all the groups that student is a member of, which does in fact confirm the output from the group command that we saw earlier. Just for reference, let's take a look at the gshadow file. In reality, you're very unlikely to use this in your day-to-day anything. but it is good to take a look at it so that you can see the similarities. Since it is root owned and not readable by my user, I once again had to use sudo and put in my password. As you can see, it's basically the same list, but there's an exclamation point instead of an X, and there are no group numbers present in the file. All of this is important because you use groups for access control, primarily for files, but also for utilities like sudo. We'll take a look at files first. With the directory listing here, you can see that the first column and the second column highlighted both say student. The first column is the owner, and the second column is the group. So just for reference, I'm going to add a new group called group2 using that command, and you'll see that it was added with the new GID, or group ID, of 1001. Taking a look at the group file, you can see that it was added to the end, as we would probably expect. Next, we're going to take one of the files from before, the trees file specifically, and change the group ownership so that it reflects the newly created group 2. From this listing, you can see now that the second column has changed to group 2, and that indicates the primary group ownership. What this means is that, if we want to, members of group 2 can have special access rights to this trees file above and beyond what everyone else would normally have. The easiest way to do that is to let them have write access, which is what I'm setting up now. With the before and after, you can see that the original file permissions were read, write, and read. And then I ran this command, which is the chmod, or change mode command, and then afterwards they became read, write, and then read. For a little bit further explanation, the first area shows that the student user has read, write permission. The second area shows that the group 2, has read, write permission. And then the last area simply shows that everyone else can only read the file. That means they can't save to it, and that they can't move it, delete it, really change it in any way. To continue exploring this, we need to learn about the chmod command, or as some people say, chmod or change mod. What it does is allow you to change the permission bits on any individual file or directories. So in this case, here are a few examples of what you can do. As we drop back into the terminal, you can see that we're going to go ahead and first get a listing of what I've got. And there's a file with read, write, and read permissions, as we've previously discussed. The first thing I want to do is set the executable bit for the user that owns it, which is student. You can see two things here. First, there's an X added to the first column, and secondly, the trees line has turned green. On colored shells, that means that the file itself is executable. This next command is going to remove read permissions from everyone to this file. You'll notice I've used a different syntax with the A, which means all, and then immediately read permissions are gone from the trees file. This also demonstrates that the permissions are completely independent of each other. You can in fact write to a file without being able to read from it, or execute something like a shell script without being able to read from it also. We can completely remove all permissions using this command, a-rwx. You can see the line is now completely blank for the permissions, and if I try to open the file using the cat command, it fails. So I now have to re-grant myself permission using u plus r, and then afterwards I can cat the file like normal and see everything that's in it. Finally, in the permissions mask, we have something called the execute bit, which unlike the other two doesn't necessarily control access to the information in the file. It controls access to what you can do with the file. Specifically, the execute bit is what marks a certain file as being executable by the operating system. So if you write a script or if you have a compiled program, this is what makes it so that you're actually able to run it. As a quick example, a couple seconds ago I wrote a shell script, and as you can see here from this listing, it is not executable at this time. What it looks like is this. It's a simple echo, and it's written in a bash script. If you try to run it, you get a permission denied. But when you set it the execute bit, which I applied to all users here, and then try to run it, it echoes the correct string as expected. And as you can see, it now has +X set for every person. Everywhere outside of your home directory, the files are going to be owned by someone else, but it doesn't mean that you can't run the files. So in /bin, the entire directory basically is owned by root, but it has the +X attribute for every file, which is why you can run something like bash, bunzip2, or bzcat without owning the file directly.